have completed chapter number 3, and now we'll be moving on to chapter number 4. Chapter number 4 is basically related to the fluid kinematics, and it is the advanced description of the fluid kinematics. So we'll be discussing different flow descriptions in this chapter. We'll discuss about the material derivative. We'll discuss the Reynolds Transport Theorem, and then we'll discuss about the continuity equation, linear momentum equation, and the energy equation based on the Reynolds Transport Theorem, which is chapter number 5 of your book. Okay, so continuum hypothesis, we have already studied this. What is continuum hypothesis? We have discussed this in detail in the start of the course. What is continuum hypothesis?
A particular system or particular area of the system में जहाँ पे measurements वगैरह करेंगे.
We have
So
discussed
considering
that.
a particular property, considering a particular property to be continuous throughout a particular volume.
Yes, basically solids, we have discussed that solids are rigid, right? Solids are usually rigid, and their properties, they behave as a continuum. They behave as a fixed mass, right? They are continuous. Their properties are continuous throughout. But in liquids, the molecules are more free to move, or in gases, the molecules are extraordinarily free to move. They are not bound together. They are rigid. So in order to define a property, we need to consider the behavior of the fluid as a continuum behavior. That is, we define an area or a volume, and we consider the property or the average property in this area will be the property of the whole fluid volume, right? This is the basically continuum hypothesis. Is it clear?
Yes.
So
Yes, sir.
generally speaking, if we talk in more elaborate way, it is difficult to measure property at each fluid molecule, right? If we have a large volume of fluid and we want to measure the property, then what can be the way? One way can be that we tag each molecule, we measure it the property for that molecule, and then we take the average of those properties. That is very difficult. So we define a certain area. We see that this is our continuum, fluid continuum, and we measure property for that continuum, and we say that okay, the whole average property for that volume, and we say that whole liquid volume will behave or will have that value of the property. Clear?
Yes, sir.
Yes, sir.
So the motion of the fluid is determined by its velocity and acceleration of the particle. So the motion is always defined by velocity. So velocity is a very important property for any fluid motion. And we know that the fluid properties change with location as well as with time. Let's say we can write here. Fluid velocity, let's say if we talk about the velocity, it will be function of x. It will change in the x coordinate, it will change with y coordinate, it will change with z coordinate, and it will also change with time. It can be steady or unsteady. There can be change in the velocity with respect to the time as well. There can be change in the velocity with respect to the location, that is x, y, z coordinate. So there is spatial component. This is called spatial component, and there is a time component as well. So every fluid property depends on the spatial coordinates, space coordinates, and the time as well. So whenever discussing fluid properties, we need to be sure that okay, how the fluid property is varying. Is it varying with the location, or is it varying with the time, or is it varying with both? Okay, is it clear? So let's say if we talk about the temperature will also be a function of the space. How it can be a function of space? Let's say if I measure temperature at, let's say this is fluid volume. I measure temperature at this location, I measure temperature at this location 2, and if I measure temperature at this location 3. So T1 is at one location, T2 is another location, and T3 is another location. And if I say, okay, this fluid volume is located in two-dimensional space, which is xz space. So I can see that x1 and z1 are different coordinates, x2 and z2 are different coordinates, and x3 and z3 are different coordinates, right? And the value of the temperature is changing with these coordinates. So temperature is a function of the space coordinates x and z. Clear?
Yes, sir.
अभी
This
temperature सर time and time का भी हो सकता है सर, क्योंकि सर सर एक जगह पे हीटर वगैरह चल रहा है तो
let's
सर टाइम के साथ
I'm coming to that point as well. These values I measured at, let's say, 12 o'clock, 1200 hours in this space. I again measured these three values at, let's say, 1210 hours, which is basically after 10 minutes. And I see that the values have changed to other values, like T1 has changed to T1 dash and T2 dash, and the temperature has increased or decreased at these points. So what has happened? There is change with respect to the location as well, and there is change with respect to the time as well. Clear?
yes sir.
Yes, sir.
So the properties of fluid will generally be a continuous function. So we need to define a continuum in order to have the velocity, in order to have the fluid properties well determined. Okay, all right. So we're discussing about the continuum hypothesis, and now in fluid flow or in any motion like that, even that of a rigid body like a solid or a particle, the most important field is the velocity field, or the most important property is the velocity. If you are well versed with the velocity, or you know velocity, you can gather much information about any fluid property if you know about the velocity. So in fluid, we define the velocity field like the one shown on figure. Velocity is basically a function of the position as well as the time. It's the function of the position as well as time. Let's say we have particle A whose initial position is, let me take it to the, so let's say we have this particle A whose initial position is defined by this position vector R, Ra, and this R is function of time t. This position A is defined at some time t. So this position is, let's say, xa, ya. There will be no z because it is in the xy plane, right? After some time delta t, this particle is following this path and it changes this path. So now the position is xa1, ya1, za1. So we can see that the velocity is a function of the location as well as the time. So we cannot simply define the velocity like the one we used to define that okay, velocity is dx by dt. Now the velocity is function of three position vectors. The velocity itself is a function of three sub-vectors, that is the velocity u, the velocity component v, and the velocity component w. Clear? So we'll write the velocity vector now as here. The velocity vector v would be equal to ui plus small vj plus wk. This capital V is representing the velocity vector or the velocity field. The small components are the velocity components along I, j, and k directions. And each of these components is itself dependent on the x, y, z direction and as well as the time. Clear? U is dependent on x, y, z, and the time. Similarly, v, small v, the second velocity component along the j direction is dependent on x, y, z, and time. Clear? And similarly, w, the third component, which is along the k direction, is dependent on the x, y, and z, and the time t. Clear? Now you will be asking how is it possible that component that is along the x direction is dependent on the y and z direction, let's say about u. That should be your question. Or your question should be, okay, the component located along the j direction or the y direction is dependent on the x and z direction. And what about the third component? So if it is clear to you, how can you explain it? Is it clear to you? The velocity field, the velocity vector?
सर ये इसका मतलब यही हो सकता है कि टाइम के लिहाज से ये इसके कोऑर्डिनेट्स पर चेंज होंगे.
Just with time there will be change in the u vector, or if I simply write u is equal to, let's say, x square plus y plus z cube by 2, and z is multiplied by t as well, z cube t by 2. So this is the u. Similarly, v can be another function. Let's say that is x square t plus z. There is no y involved, let's say. And w can be another function, that is y square plus t square by 2. Let's say this is just a random function I've written. So the velocity vector would be x square plus y plus z cube by ti plus x square t plus z into j and plus w, which is x square plus t square by 2 into k. Clear? So these all components are function of the x, y, z, t, because the position vector which is defining them is again a function of the x, y, z, and time. Clear?
Yes sir, clear.
The magnitude of velocity would be equal to simply the magnitude of a vector. Like for calculating magnitude of velocity field v, we'll take the square of these u, v, and sum of the squares of the u square, u, v, and w, and take the under root u square plus v square, like you calculate the magnitude of any vector. Okay, the magnitude of this velocity will be calculated like this.
सर काइंडली एक दफा ये ऊपर आपने जो लिखी हुई है इनको काइंडली एक दफा एक्सप्लेन कर देंगे इक्वेशंस.
Equations, we'll be discussing these in detail in the coming chapters, and we'll be discussing about the material derivative and the Reynolds Transport Theorem. We'll be discussing these. I've just given a simple example, okay, how u, v, and w are dependent on x, y, z, just to explain, okay, this can be sort of a dependency, okay.
Okay, sir.
Now, in order to define flow field, there are two types of description. Like we need to be sure, okay, which type of description is being used. There can be Euler description and there can be Lagrange description. There can be Euler equation and there can be Lagrange equations. These two are like, Euler approach is that the fluid properties, any of the fluid properties written as a function of the space and time, x, y, z, and t. And if you want to calculate about any fluid property, or if you want to determine at any fluid property at any point, you fix the points in the space as fluid flows through that point, and the information is gathered from different particles pass through that location. This is called the Euler approach. If I explain it simply, let's say this is some fluid flowing in a, let's say this is a river, okay. Now we know that the velocity of the river is a function of the location as well as the time, right? Euler approach says I place sensor 1 here, I place sensor 2 here, I place sensor 3 here, I place sensor 4 here along the length of this river. And each of the sensor is measuring velocity. Let's say the sensor 1 is measuring v1, this is measuring v2, This is measuring V3. This is measuring V4. Now the location is fixed for measuring velocity, right?
Yes, sir.
But these values will be coming to me at different times. V1, every particle, let's say there is a particle A, it will pass from this location, its velocity will be measured, then it's passed to this location, velocity will be measured, then it's passed to this location, velocity will be measured, and then it's passed to location 4, velocity will be measured. After this, there is a particle B. So I have all the properties of the particle A with change in location and with change in time, because it will take some time for particle A to travel from point 1 to point 2, right? Then point 2 to point 3, and then point 3 to point 4. So with change in time, I will have the four velocities. Let's say in 10 seconds duration, I will have 4 velocities for particle A. So I have variation of the property velocity for particle A in 10 seconds. So I have, let's say, 2.5 second instance for each. I am seeing that, okay, with every passing 2.5 seconds, how the velocity of point or the particle A is changing. Then there is another particle B behind this particle A. It will also pass through this location, and I will have same readings for this. So I will have flow behavior at different locations with time as well. This is the Euler description. Is it clear?
Yes, sir.
This is just like that. Let's say you are standing on a road and different cars are passing in front of you. From your location, you see one car passing in front of you. You say, okay, its velocity is 100 meters per second. Behind it, and there is another car. You keep standing on your location and you say that, okay, the velocity of the second car is 80 meters per second. Then there is a third car and you say the velocity of this third car is 150 meters per second. Then is the car 120. So you are fixed at your location. You have fixed the location and the particles are passing from that location. With passing time, you are calculating the velocity of each car in front of you. Clear?
Yes, sir.
This is called
Yes, sir.
the Euler approach. You fix your location and you measure the property for different particles passing from that location. The Lagrange approach is altogether different from this. Now what you are doing, you are not standing on the road, you are sitting inside a car. And when that car is traveling, you are measuring, okay, initially this car is moving at, let's say, 100 meters per second, then this car is moving at 20 meters per second. So you're moving with the car. You are sitting inside the car and you are noting its velocity. This is the Lagrange approach. Now, instead of being at a fixed location, you are moving yourself. So what are you doing? You are tagging the particle basically. So in a Lagrange approach, I will place the sensor on this particle A, and wherever it will go, I will have its data. I will have its any property which I am measuring. Is it clear?
Yes, sir.
So the difference between the Lagrange approach and the Euler approach, is it clear? Lagrange approach is moving with the particle.
यस सर, लेकिन ये जो आप लेग्रांज वाली जो सेकंड आपने कही थी वो प्रैक्टिकली पॉसिबल है उस तरह से मेजर करना?
Is that the question? Let's say you want to tag particles. Basically, you want to place sensor on the particles. For large bodies, it is possible. Like, let's say if it's a car, I can place a sensor on a car. If it's a aeroplane, I can place a sensor on an aeroplane. But for fluids, it is not realistic to tag.
यस सर, ये पूछना है मुझे.
Lagrange approach is beneficial in experimental work.
Okay, sir, understood.
What you can do is, let's say this is a stream of fluid flowing, and you want to see how a particle will move in this stream of fluid. What you do, you take some color, some dye, okay, and you put it, you make a hole here and you insert it in this flow line. What will happen? That color will start following a path. So what is this? This is the Lagrange description.
Lagrange approach.
Or what you can do, you can take a ball, place sensor in it. Let's say there is a temperature sensor in this ball, and you put it in it in this flow line. So this ball will be moving. So the reading from the sensor will be temperature sensor along this flow. That is the Lagrange approach. For either approach, what you will do, you will place sensors along this flow line and you will measure different values. Let's say if you want to measure temperature, you will place temperature sensors. Is it clear? The difference between the Euler and the Lagrange approach?
Yes, sir.
So it is generally more common to use Eulerian approach to fluid flows. For example, measuring water temperature or pressure at a point in a pipe. So जो आपका question था, that is cleared. So Euler approach is more preferred because of its simple nature and more realistic approach. Lagrangian methods are sometimes used in experiments that are to trace the paths to determine the water currents like this. So there is an example in your book to better understand the Eulerian and the Lagrangian approach. That is the bird migration example. Eulerian approach can be, let's say, birds are migrating from one country to another. There is winter season and they are moving from the colder regions to the hotter regions. The zoologist, which is like a person who studies the behavior of the bird, he gets his binoculars and stand at a point and start seeing the birds. Okay, 1 bird, 2 birds, 3 birds, 4 birds, and at the end he can say, okay, this much amount of birds have passed from this country to this country. This is Eulerian approach, that he's standing at a fixed location and he's counting. The Lagrangian approach is, what did the scientists do? They captured the birds, they put radio transmitters on those birds, and those radio transmitters will be transmitting the location of the birds. So they can simply know, okay, how much birds have moved from this country to other and which path they have followed. This is the Lagrangian approach. Lagrangian approach is very much sophisticated. It will be giving you full information about the path of each particle, but it is more difficult to implement on a fluid flow scale, on a micro scale, on a fluid level. Eulerian approach is much more simple, but it's a more general approach. Is it clear?
Yes, sir. और I think Lagrange जो approach है इसको हमें मतलब systematic करना पड़ेगा ज़्यादा, because वो जो अभी आपने जिस तरह example दी थी birds की, तो उसमें ये कि मतलब उसमें extra जो environmental factors हैं वो भी add हो सकते हैं.
Definitely, that's why I'm saying it's more sophisticated. It's more sophisticated. It's more complex as well. We can take another example to better understand the Euler and Lagrange flow description. You are well familiar with the chimneys.
Excuse me, sir.
Yes.
सर लेकिन Lagrange उस अप्रोच से हमारे पास ज्यादा एक्यूरेट आंसर्स नहीं आएंगे, क्योंकि हम अगर टैगिंग के जरिए सर करते हैं तो
सर it is difficult to tag molecules.
Yes, sir.
With the modern technology.
But sir, I'm just talking about accuracy.
You are thinking from a frame of mind of, let's say, a person who is talking about materialistic things like cars, automobiles, aeroplanes, or things that can be materialistic. But on a fluid scale, on a molecular scale, yes, Lagrange approach will be accurate, but that can be accurate on a scale that is physical, that is measurable. But what about the fluids? What about the molecular level? What about the nanoscale or the microscale? Can you capture a molecule, put a sensor in it? No, that's a much difficult task.
Yes, sir, understood. Okay.
We take another example of a chimney. Let's say there is a chimney of smoke. Like you are, let's say, standing near a brick nail, the industry where bricks are made. So you see a chimney, and from that a smoke is rising. So now you are interested in measuring the temperature of the smoke or the residue coming from the chimney. There are two approaches. One is the Euler approach and the other is the Lagrange approach. In Euler approach, what you will do? You will place sensors
on the
chimney, on the exit of the chimney or different locations on the chimney, and you will gather that data from that sensor, and you can say, okay, with this rise at this location, the temperature was this. At this location, the temperature was this, and after this much time, the location of these temperature points changed like this. Or the Euler approach can be, this is the Euler approach, and the Lagrange approach can be, you tag a particle in the smoke and you let it travel from the bottom of the chimney to the top of the chimney and then into the atmosphere, and you install a sensor on that particle and you measure, okay, with location and with time the temperature is changing like this. Okay,
Yes, sir.
Okay, sir.
so we will be mostly using Euler approach, but we can switch between the two approaches. Like if we have information about the one approach, and if we know some information, we have some translating function that can help us to translate from the Euler approach to the Lagrange approach, or from the Lagrange approach to the Euler approach, then it is possible to convert the result. So we use Euler approach for collecting data, and then with the help of our transfer function, we can write it in the Lagrange form as well. Let's say if we also know position of each particle as a function of time, we can translate Lagrangian information into the Euler information, and reverse is also possible if we install sensors from bottom of the chimney to the top of the chimney, like throughout the chimney. Let's say this is the chimney. This is the chimney, and we install sensors, countless sensors from this bottom to the top. Now the data or the transfer function or the temperature variation we'll have from this will be equivalent to a single particle tagged that moves from this point to this point, right? So the two approaches will be comparable. Clear?
Yes, sir.
Yes, sir.
So it is possible to convert between the two descriptions, the Lagrange description and the Euler description. So if we are clear about the Euler approach and the Lagrange approach, then we can further define the streak lines and path lines. We are already familiar with the streamlines. We will discuss with this what is streamline in further detail, and streak lines and path lines. Streamlines, streak lines, and path lines basically used in visualization of flow. And when we talk about visualization, then it means it is the experimental work. It is more towards the experimental side. But we have also seen that the streamlines are mostly used in the analytical work. That is, we have discussed in the previous chapter that streamlines help us to visualize flow analytically as well. But streak lines and path lines are purely related to the experimental work. When you are performing experiments, you are interested in drawing the streak lines and the path lines. So we
Yes,
can.
sir.
So what is a streamline? Streamline is tangent to the velocity, or the velocity is always tangent to the streamline. This we know from the very basic understanding of the previous chapter. For steady flow, the streamlines are fixed in space. For unsteady flows, streamlines vary with time. So we have discussed that for steady flows, streamlines are fixed. They do not change with time. But for unsteady flow, streamlines may vary with time. And slope of the streamline is equal to the tangent of the velocity field. Let's say there is a velocity field. So, and it's a two-dimensional velocity field. So this is a two-dimensional flow. This blue line, dark blue line, is representing your streamline. And we know that velocity is always tangent to the streamline, right? So this purple line is representing your velocity field, and it is tangent to the streamline. And we know that velocity field is now for a two-dimensional flow. For two-dimensional flow, velocity field will have two components, the u component and the v component. Let's say the velocity vector v would be equal to ui if this is the xy flow, if it's the xy plane in which the flow is happening, vj, right? So if this is the velocity vector, the horizontal component would be u component and the vertical component would be v component. This is u and this is v. Clear?
Yes, sir.
So if I ask you, what is tangent to the streamline?
V.
That is basically dy. The slope of the streamline would be dy by dx, right?
Yes, sir.
And that would be equivalent to the slope would be equivalent to this
Velocity.
V by U, ratio of V by U, right? Clear?
Yes.
So dy by dx is equivalent to V by U. So the slope of the streamline is equal to the tangent of the velocity field. The tangent of the velocity field is dy by dx, which is basically V by U. Clear? So this is the
Yes, sir.
imitation of the streamlines. The streamlines can be determined from the velocity field by integrating the lines defining the tangents of the velocity field. So if we have the tangent lines, we can define the streamlines. Like if I know tangents at all the location, I can draw the streamlines because we know that velocity is tangent to the streamline. So that's just a theoretical concept. The streamlines about different flow have been visualized and have been discussed. Like around an aerofoil, you will find streamlines like this. Streak lines, that's more important concept. Streak line basically consists of all the particles in a flow that have passed through a common point. They are mainly a laboratory tool. How they are drawn, let's say, this is a flow situation, this is a pipe in which there is certain flow, let's say, is happening. There, this is the flow line. What you do is you take a camera. This is the camera. And there are different particles. Let's say there will be one particle, this line, there will be one particle. And whenever a particle passes this camera, you take a snap, you take a picture. And then you combine all those pictures. The resulting lines will be your streak lines. Clear? Is it clear?
सर आपकी आवाज
Yes,
कट
sir.
गई सर दोबारा बोल देंगे सर ये कैमरे से बात तो आपने बताया
Basically, streak line is drawn when all the particles have passed through a same location. Okay, when all the particles have passed through a same location. So what you do, you install a camera at a certain location, and the first particle passes, you take a snap, then second particle passes, you take a snap, and the third particle you take a snap. And when you combine those snaps in order of time, the first snap at the first location and then second snap, then third snap, the line which you will get, it will be called a streak line. Okay, or in a more simplistic way, let us see
सर
that for steady flow, the streamline is exactly the streak line. Streak line is exactly the stream for a steady flow because all the particles will be following the same path. So the streak line and the streamline will be same thing. Is it clear?
Yes, sir.
Yes, sir.
For unsteady flows, particles injected at the same point at different time need to follow the same path. No, they will not follow the same path for unsteady flow. All the particles will be following all different paths at different times. So instantaneous photograph, the marked fluid would show the streak. The streak line would not be same as the streamline for unsteady flow. Clear?
Right, sir.
And path line, the simplest thing that the path followed by a single particle. You mark a single particle and wherever it goes, the path drawn by it will be the path line. Okay?
Okay, sir.
So streamline is the line along which the velocity is always tangent. For steady flow, streamline and the streak lines are the same things. For unsteady flow, streamline and streak lines are different things. Streak lines are those lines that are drawn by marking the location of all the particles passing through a single location. And path line is the path followed by a single particle. Is it clear? Any question in this?
No, sir.
Okay. Next is the material derivative. In Euler approach, the fundamental property is the velocity field. Using the velocity field, we can get information about any fluid. Like we can completely define the fluid motion. So What is the analysis description? We have already discussed that it does not track the behavior of individual particles. It describes the velocity of whatever happens at a given location. So what is happening at a given location is described by using the Eulerian method. So if we consider again that same particle A and we consider its motion, we see that its velocity is a function of time as well as space. So the velocity field can be defined using this velocity vector, which is VA is function of V and which is function of location. Location is function of again time. Clear? So
Yes, sir.
Yes, sir.
if I say that VA is the velocity of the particle A and this VA is dependent on location X, which changes with time, right? It is function of location Y, which changes with time. It changes with Z, which is function of time, and this velocity itself changes with time. Clear?
सर स्टेडी स्टेट फ्लो के केस में सिर्फ पोजीशन पे डिपेंड करते हैं वेलोसिटी टाइम
फ्लो केस में तो फंक्शन आएगा ही ना। स्टेडी फ्लो में तो अभी जनरल डिस्क्रिप्शन, अनस्टेडी फ्लो की बात कर रहे हैं, ठीक है। अभी हम स्टेडी फ्लो के केस में तो टाइम खत्म हो जाएगा, देयर विल बी नो चेंज इन प्रॉपर्टी विद रिस्पेक्ट टू टाइम। सो द वेलोसिटी इज फंक्शन ऑफ x, y, z and time, and each x, y and z itself is a function of time. Is it clear? So if I ask you to
Yes, sir.
calculate the acceleration AA, what you will do, you will say, okay, take derivative of the velocity A with respect to time, right? ऐसा ही कहेंगे,
Yes.
but now this velocity is a function of location as well as time, and that location is further a function of
Function of time.
time. So this derivative is not that much simple, like a simple derivative. Okay, take the derivative of the velocity. So when you will take this derivative, what will happen? You will have to take the derivative of this VA with respect to time and with respect to the location as well. Clear? So first we write this velocity is dependent on time. Okay. So we'll write partial V A by partial T, right? Because of the dependency of this velocity on time. Clear?
Yes, sir.
Yes, sir.
Then we'll have to write partial by partial T of VA into partial X, sorry, not, we have to write partial. Then because this velocity depends on this XA, so we'll have to write partial VA by partial X, and this X again depends on time, so we'll have to write its derivative partial XA by partial T. Clear? Then further again the dependency of this V on Y and then dependency of that Y on T, partial V A by partial YA into partial YA by partial T, and similarly about the Z, that the dependency of this V on Z and then that dependency of that Z on T. So partial VA by partial Z A into partial ZA by partial T. Clear?
Yes, sir.
So this is the point where we leave today, and we'll discuss in the next class in detail about these components. We can see that each of the time component is again representing partial x, partial t representing the x component of the velocity. Let's say UA, which is the UA component. Partial YA by partial t representing the y component of the velocity field, which is, let's say, small v into A. And this partial ZA by partial t is representing the k component or the z component of velocity, which is, let's say, WA. So acceleration is basically partial V. This is the whole velocity or the velocity field, its derivative with respect to time t, plus u component of the velocity or the I component of the velocity into derivative of the whole velocity field VA with respect to time, with respect to the spatial coordinate XA, plus the velocity along the y direction into the derivative with respect to y along the whole field. Plus W, which is the z component into the derivative along the z direction of the whole velocity field. Clear? Any question in this?
सर ये पहले तो हमने लिखा है ना पार्शियल v ओवर पार्शियल t, तो फिर सर इसमें सर ऐड किया पार्शियल v ओवर पार्शियल x और पार्शियल x ओवर पार्शियल t. सर इनको अगर पार्शियल x कैंसिल करें तो वही टर्म है जो पहले
Cancel
हमने
नहीं.
ऐड किया.
No, we cannot cancel
सर
that.
अगर
That is not
सर मतलब
like
अगर
that. That's a function.
जी
That's
सर.
an operator. Operators को आप cancel नहीं करते आपस में. This is basically because
सर
of
वो
the chain rule. अब थोड़ा सा अगर आपने
जी
चैप्टर
सर.
नंबर 3 में भी याद हो आपको, तो हमने एक चेन रूल पढ़ा था. थोड़ा सिंप्लीफाई करते हैं. V is a velocity function and it is function of x and t. ठीक है? And we further say that x is function of time. ठीक है? So if I ask you to calculate acceleration, you will calculate dv by dt, right? तो मैं 3 फंक्शन से 2 फंक्शंस के ऊपर हम डिस्कस कर लेते हैं, like this. So if I take derivative of velocity with respect to time, I will have to take partial v by partial t, right?
Yes sir.
Then I know that this velocity is a function of x. So I will have to take this derivative with respect to x, because this d is basically now applying on this whole function. But I see that x is also a function of c, so t. So this will be partial x by partial t to the variable. Clear?
Yes sir.
और ज्यादा इसको सिंपल समझना चाहते हैं तो let me break it for you. We are applying d by dt on 2 functions, which is basically v of x and v of t. ठीक है? ऐसे ही है जी. अगर मैं इस तरह लिख लूं ब्रेक करके थोड़ा सा,
अब
तो पहला
मेरी स्क्रीन सर रुकी.
ठीक है, ये
सर मैं
तो मैंने
सुन
लिखा
रहा
है
हूँ.
यहाँ. ये नजर आ गई.
यस सर. सर अब
अब इसको अगर एक्सपेंड करें u इंटू वी वाली फॉर्म से, t बाई डी टी u इंटू वी फॉर्म, तो आपके पास यही रिजल्ट आना चाहिए। जस्ट करके देखिएगा, ठीक है।
जी सर।
अगर इसको फिर नेक्स्ट क्लास में हम फर्दर एक्सप्लेन कर लेंगे, वी विल फर्दर डिस्कस दिस इन द नेक्स्ट क्लास, ठीक है। तो उसमें कोई क्वेरी होगी तो डिस्कस कर लेंगे। एनी क्वेश्चन, किसी और का क्वेश्चन?
एक्चुअली सर,
जी जी
सर आज का आपने क्विज अनाउंस किया हुआ था सर।
क्विज, यस, क्विज के बारे में ये है कि मैं उसको ना इसी वीक में होगा। नंबर 3 आज हमने कंप्लीट कर लिया, ठीक है। तो कंप्लीट चैप्टर 3 से होगा। ड्यूरिंग रेगुलर क्लास टाइमिंग मेरे लिए थोड़ा सा करना मुश्किल है, क्योंकि इस टाइम पे मैं उसको कर नहीं पा रहा। तो आई विल बी कम्युनिकेटिंग इट टू योर सीआर, प्रॉब्ली इट विल बी ऑन फ्राइडे को होगा, लेकिन किसी आपकी रेगुलर क्लास टाइमिंग में नहीं होगा, ठीक है।
एक्चुअली सर,
जी सर।
सर मैंने ट्रैवल करना है सर, मैं नेक्स्ट डे से अवेलेबल नहीं होऊंगा सर। फिर आप मेरा अलग से या किसी और के साथ दे सकते हैं सर आप?
वो फिर हम एंड पे, आप उसको मिस कर दीजिएगा, एंड पे हम उसको काउंट कर लेंगे, ठीक है। दैट वो किसी एक्स्ट्रा क्विज के
ओके
अंदर,
सर,
ठीक है।
ओके
तो फ्राइडे को आपकी रेगुलर क्लास टाइमिंग में नहीं होगा, किसी ऑड टाइम पे होगा, बट आई विल